Yeah, okay, so, hi everyone, my name's Dan, for those who don't know me, and I'll be talking to you a little bit about auditory neuroscience, developmental neuroscience, and cochlear implants. So, I won't go too much into how we hear, since I'm sure you'll remember. Sound comes in from the outer ear, gets introduced in the middle ear, then comes to the inner ear, where the organ of corti is, which then sends it further on into the brain. Specifically, the pressure comes from the middle ear, that the sound is introduced into a pressure wave, comes along the fluid, and then moves the various inner hair cells, which create the neural impulses which go up the nerve fiber. And another point which I'm sure you all completely remember, to the topic mapping, the various frequencies of the sound spectrum will basically have a physical mapping along the organ of corti itself. High frequencies in, low frequencies out, so on and so forth, and which is one of the reasons why it looks like a squid. So, that's how it normally works. Now, what happens which can cause loss of this sensory function? Not a loss of causes, unfortunately. Everything from disease, meningitis, genetics, damage due to environmental factors, extreme noise. The hair cells were thought not to regenerate. Now it's a matter of some debate, actually. But basically, they're very, very, very vulnerable. And if you lose the inner hair cells, you go deaf. Lose the inner hair cells, you lose your hearing and also level of deafness. So, hearing loss is a spectrum, of course. There's levels of intensity. And by the way, you all remember that we're talking here about amplitudes, although it does change with the frequency, since we're more sensitive to the frequencies associated with sound and speech. But generally speaking, beyond about, say, 40 decibels level, it starts to be noticeable, and beyond 75 to 85, it's considered extremely severe or profound hearing loss. Again, log scale. So, the more points you go up, it's a massive, massive difference in terms of the volume. Now, for a moderate or classical case of either not extreme hearing loss or just about history, the classic treatment is hearing aids, which quite simply amplify the ambient sound, so you're getting more sound in, so even if you can't hear someone else there shouting, this gives you the benefit of having everything around you shouting at once. Wonderful solution, but it really does work rather well. There are even some elegant classical cases such as this chair fit for a king. Really, it was literally for a king. It's still possible. Now, the problem is though that all of these cases that works, as said, when the hearing loss is not too extreme. So what happens when either, for example, say someone has lost the majority of their inner hair cells, which means that they're just completely deaf, there's no mechanism to transduce it, or that say the overall level of damage is very, very high, most of the outer hair cells and most of the inner hair cells, so they can't hear above 90 unless it's at least 90 decibels, in which case amplifying doesn't work very well. This is, by the way, the level that discuss around what's called profound to severe hearing loss. So in that case, that's where the cochlear implants come in. What they do is really, instead of just amplifying the input, they replace a bunch of the actual signaling process itself. They replace part of the biological process. So the implant is made out of two components. One is an external part, which is just a microphone, takes in the various sounds in the environment, also processes it. It focuses on various parts of the spectrum, since we know what parts of the spectrum, say, sounds are human speeches, the various phonemes which make up various human languages, so it focuses on them and amplifying them as opposed to ambient sound, which again is a big problem, since there's a lot of noise going around that normally we can filter out. But basically it takes that, focuses on that, transduces it using various singular processing techniques, everything from fast Fourier transforms, the stuff taken from the sonograms we discussed, and then that pipes it into the inner part of the implant, which is implanted surgically, by the way, which is a receiver which pipes it in to the real meat of the process, which is inside the organ of corti itself. What they have is basically this big, effectively curved tube, which has various stimulating electrodes implanted along it. Now, as you all remember, the mapping of the organ of corti is just based on frequencies. So, if you take the sound, you know what its frequencies are after decomposition. So, all you need to do is activate the various parts of the organ of corti which correspond to that frequency, say here and here for a certain sound, and there you go. You see the same activation as the sound. Now, so again, just to show you how it works, normally the inner hair cells would activate the nerve fibers given the movement. So here with the organ, it's just the microelectrode nearby activates the nerve fiber directly. Now, the thing is though, it's not quite as simple as that. Although it is a massive improvement. I mean, we're talking about here, it's the solution is not as because in mild it's not as good as what we had going naturally for people who can hear normally. For one thing, by the way, this process pretty much shears out the hair cells there. So again, it's only used for people who are really severely deaf, since it's a very destructive process. Furthermore, for one thing, can't cover the whole range of frequencies in terms of the organ itself, since it can't reach all the way in. It also has a very small amount of channels. It has about, the modern ones have around 20 electrodes. The technology has been around, by the way, since 1970s. But unfortunately, as we saw earlier, it stimulates in somewhat in a gross way, as opposed to here, where it's very, very sensitive. Here, it's stimulating a chunk, and also this will interfere with that. So again, although it has been improved with, say, biphasic stimulation, you're still talking about very high levels of electrical noise. Also, remember, the whole fluid there is extremely charged, so it's even worse. It's activating various electrodes inside the superconductive fluid, basically. So you get even more noise. So we have, let's say, 10 effective frequency channels. Naturally, for what you're hearing now, you have about 3,500 in a hair cell, and that's further amplified by all of the outer hair cells. So we're talking about something which is a fraction of a fraction of a fraction. And that's even ignoring the fact that even with various compression techniques and the like. Thing is, though, there are more limitations than just purely sensory. Then, by the way, this is the example you heard from class. I'm sure you remember how it's nothing the same. But still, the fact that there are many factors infecting how effective the implant can be. Now, the main one, of course, is quite simply how long the person was deaf before the implant, and also what age it comes in. And this is actually even more important than how good the implant itself is. It's again more modern technology, more electrodes, more channels, better processing improves it, but there's more to it than that. And by the way, there are more factors. There's therapy, training, tuning the various channels of the individual, stuff like that. But still, though, you could say what's more important than this implant itself is the age of the individual. Why does that matter so much? Okay, as we all know, all of the various sensors, the input we get in, there's a lot more to it than just getting, sound comes in, or I see something and I know what it is. There are a lot of steps that go for the cortex, both of there's processing and computation done at the sensory level, but also the ascending pathways, intersections, other parts of the brain itself. And the problem is that when you have someone who is deaf from birth, who gets the implant, then it makes a very big difference at what age they get it. Why? So this is the more slightly more developmental neuroscience part of the story. So, in a young brain, a baby's, for example, the whole system of the brain is just set up in a very different paradigm. It's a state of, trying to prune out as much as possible, get rid of everything you can, try to find if there's anything relevant and maybe keep it. But it's in the setting of, okay, we don't know what's going on, let's try to fire everything. If it works, then keep it. If not, shut it out. This is the period, if anyone remembers, up until the age of 2, you're talking about half of the synapses that the baby is born with being dropped out, and also other various differences on the functional level. Now, in that sense, we're going to talk slightly about, by the way, don't take this example as the exam, because it's a very, very gross definition. So, in that sense, and that said definition is experience-dependent plasticity. So, as we all know, also from Paul and Wizard, we have various circuits which are dependent on external input for their function. So, for example, you have some various systems which don't need this. We all know how to breathe, and we all know how to make the heart operate, and we don't need any external input for this. But other circuitry require an external input or interaction with other systems in order to function properly or can be modulated. For example, the ability to identify different sounds or other people is something which is experience dependent. I can learn to recognize what an elephant is. I can't, although I don't need to learn how to breathe. And by the way, all of these various experience dependent plasticity in terms of the circuits in the brain function is massively different over periods of time between organisms in the circuit. It's huge, huge, huge field. So, specifically when we're talking about experience dependent plasticity, we have, you could say, various periods in some of these circuits. Some of them have, say, periods of sensitivity, which are various periods in which a circuit, which is experience dependent, is just massively more sensitive. It's much more receptive to external input. So it's a period when it's something which can be changed, but at any point in life, but during this specific specific period, which by the way is not necessarily right after birth, although it's usually some time after birth up until, say, the equivalent of adolescence, effects of strength enhanced. So what's a very good example? Say, learning languages, specifically secondary languages. A baby can learn 3 languages at once from its parents while doing everything else at once. If I were to try to study now Portuguese, German, Spanish, and French at the same time, then it would be really, really hard, and it would take me many, many years to reach a decent level of proficiency. But I could do it, possibly. But it would be much, much harder. But it's not a binary difference. This is opposed to, say, critical periods, which are, for some circuits, you could say they're experience dependent for only a limited period of time. That is, they have a certain window of a certain time frame in which they can receive input, they can receive their instructions and tuning, and afterwards they lock and remain relatively stable. So a very classical example is filial imprinting, where given a slight period after birth, what you see the most, you know that's your parent, that you stick with it, that's your parent for the rest of your life. Another example would be songbird song acquisition, which is a rather nice example where it's in multiple stages. And of course, Google and Weasel's example with cat and monocular dominance, which is very relevant to our example here, in that, prevent the input for a certain circuit during its critical period, then the brain will know, that stuff's junk, I don't need it, give over that space to other more useful circuits and functions. While if you do it for an adult, it doesn't matter. You can take an adult cat and cover off their eye and do it for 3 years and it won't matter. Now, we can see why this would be a problem with people who are, say, prelingually deaf or born deaf. It's not as much of a problem for adults who become deaf, since they have the circuitry in place, and by going from what we know from the theory, it would remain stable. And by the way, that is in real life. They can adapt to it even though the sounds are quite different, but they have the circuitry in place, so there's more room to play around. But for people who are born deaf and then only get an implant at a later age, their flexibility and the ability to improve is very, very limited. There's a very small range of improvement which plateaus very, very quickly. Okay, but what about children? Since again, one of the great cause deafness in many children, for example, diseases of the like of them being born deaf. So there's a very big question of how early should you implant it, how much of a difference does it make, and just how crucial is it to get added in. I mean, with no prior knowledge, we might say, just let somebody hear and then learn how to hear better. But that's not really the case, or at least thus we would speculate from what we know. And as a side note, there's another big issue with this in terms of a cultural issue, that there are many deaf community as a very large group which regard being deaf as a cultural disability and not a biological disability. So they may very greatly favor only having the implant added after a certain age, after the child is comfortable with sign language and deaf culture. And I won't comment on my thoughts about that because I'm being recorded. Or possibly not. Whatever. But basically, I think it's, yeah. So at any rate, an example study is this one from 2010, in which case they really wanted to look at the effects of age at the time of the implant on how the child improved in terms of verbal comprehension and expression. Since, by the way, expression also, if you can't hear yourself, it's very hard to speak in a understandable way. If you can't hear how quickly you're speaking, or if you can't hear how well you're modulating the tone of your voice, then comprehension is very damaged. Expression. And comprehension as well. So what they did in this experiment was took groups of children, all born deaf, or the majority of them, divided them all on relatively normal kids, relatively large groups of about, say, 50 each. They split them into 3 different age groups based on age, under the age of 18 months, 18 to 36 months, that was 5 years, and also had a comparative group of children who could hear, and they really looked at the before and after a period of a number of years, of how the expression and comprehension improved for the various children, while also looking at some of the other factors. So then I measured something called a psychological scale, the Raynal Directed Language. So, again, really what they were interested in though was the question, first of all, for some reason they felt the need to show that getting a cochlear implant improves deaf children's ability to hear and speak, which I find it slightly odd in 2010, I can understand in 1990, but. And also the effects of age, which is, again, this is very important from a practical point of view. If you note that there's a very big difference between 12 months and 8 months, or the age of 2 and the age of 4, which, by the way, can make a massive difference in other things, such as autism, then we may really want to focus on an even early age of screening. So, said, they also looked, by the way, other various co-variables. Again, it's more from the field of medicine, psychology, so it's also useful for policy recommendations. So this part shouldn't be too interesting to you. We'll show it more condensed, but again, the different groups, comprehension and expression scores. The black line would be what normal hearing children would have at the same time, while the colored lines in each group, the various distributions for the various groups of children and how would they hear.
Dan, what's on the x-axis, y-axis? I can't understand this graph.
I'll be showing that more in detail in the next slide, but x-axis is really just over time, since from the start. Still 5 minutes. So, yeah, so this is just
we just started with the results, no? It's just starting to become interesting.
the results kind of summarized in one line, so I prefer the other bits. So, I'll show this now here. This is the visual expression. This is, by the way, this is just a condensation of all of these various lines. The very small lines are for the various children, and then they condensed it. And here we show it really segmented by the various ages. Comprehension, expression, normal black line is for normal hearing children. They compared it, by the way, for the various age groups. And here we see, although it's easy to see it later in the numbers form, that again, they measured it, and then they measured it after 3 years, unless I'm mistaken. And here we see the slope of the improvement after such and such time. So again, x-axis is the age. So start at the beginning of the test, for say 18 months, then look 3 years later. So y-axis is also what the comprehension score, expression score, that is how well they did. So higher is better, and what's even more important in terms of comparing the groups is the acceleration, the rate of the slope. Since again, if we go over a year and someone improves twice as much, it's much more interesting than if somebody over a year improved to, say, twice an absolute amount, but they did it over, say, 4 years. And in that regard, first of all, we can see there really was a significant impression, and for some reason...
Is that okay? So I didn't understand. So they checked them, and then you said 3 years later they checked them again. So the graph should be linear completely, right? If they have 2 dots.
They did some checkup. They did some checkup. I think there was at least one checkup exam over the period. They did 2 or 3 years.
Okay. So they checked them once, and then they checked them several times later, and they saw how.
Yeah, it was over a few years, and also this is, by the way, again, it's give or take, it's about 60 kids flipped around, and also the various age of the children within the group was different. It was under 18 months, so meaning might be, say, 17 months, but also 14 months, 13 months, so on and so forth. So it's also important to compare this and say child at 12 and a child at 16, and a year later would need to be compared to another child of a similar age group. That's just basically you can see the slide here if you're interested. The slide, the whole presentation is also online along with the article if you're interested in looking at the numbers. But again, though, here it's slightly more difficult to understand, but you can see that there is an improvement very clearly, and specifically highlighted for your convenience. By the way, this is the interesting column, the p-value. So again, that's in 0.05 or so is where we're talking significance. So what they found was, first of all, the most important factor was the age at the time of the implant. Number 1, most important, with very significant improvements for the younger age groups compared to the older age groups, even if everything else taken into account. So the one conclusion is really younger, better, much better. But other factors which they also found, by the way, were important were, for example, time spent deaf, which also matches up with what we talked about earlier. Whether you had hearing or not makes a massive difference in terms of if it's during the critical period. The brain is trying to say, okay, so does he have an ear? Does he not have an ear? Does he have an eye? Not have an eye? It's the period when it's working out whether to chunk something out. So time spent previous to hearing, since again, some of these are cases where the child lost the hearing due to disease. Also the overall ambient level of hearing, whether they could hear anything or not and how well, also made a difference. By the way, parents also made a significant difference in terms of the level of income and the parental interaction, which is something which we would frankly expect. It's basically a matter of children with parents who had more time and attention and resources to spend with them made a difference. So, interesting side note, whether the parents were deaf or not did not make a significant difference. But also, end result, clear improvement. So, overall conclusion, that slide, is that for one thing, that severely profoundly deaf children should get a cochlear implant. They recommend a unilateral one at least, though there are bilateral implants, which gives the benefit of some localization, but the overall recommendation is not to get it in both ears. Again, it's a destructive procedure, and the hope is that someday some bright young biologists will work out a way to regenerate the inner hair cells, and there have been actually some interesting studies on that in the past few years. So they say, try to leave one ear so we can make something slightly better than this. Secondly, less time spent deaf, better outcomes, so they really recommend early screening. They in fact recommend treatment as early as the age of 12 months in a different study. They would say even as young as 8 months, but FDA is earliest is 1 year, and there is very significant improvements. And finally, basically that there's of course massive amounts of improvements here in terms of both of the basic lexical technology or in terms of finding a biological solution. And another field of study there is really the fact of the plasticity in terms of the high levels of the brain being able to process the inputs. Again, it's two levels of problematicity here. One is really the input, getting it good enough and comprehensible enough, the implant, and also in terms of brain ability to understand it, which is where the implanting it at an early age is so important. And there actually has also been some interesting research in this field in terms of valproate and reopening of the critical period, but that's totally different subject. So, thank you very much. Questions? There's time.
Yes, you have 1 minute, 30 seconds.
Can we go over the data slide again?
Of course.
Like,
Which one would you like?
The one with the curves, the one before this. Yeah, so this one. So the test age is the year they were tested for their hearing comprehension.
It's looking at them over a period of time, from say they checked such and such time later.
So, for example, for the green one, why did they only start looking at it at year 2.5 instead of earlier? Because that's the time the implant was put in. But why not look at it before as well?
Okay, I'm sorry, I got that wrong. The x-axis would be the total age of the child. Sorry.
Oh, I see. So one is in months, one is in years.
No, they're all in. The x-axis is in years, as opposed to what? It's the fractions of a year.
So with normal hearing, they were able to test the child at 0.5 years, but the other ones okay, because
They can only put the implant.
right, okay.
Yeah. Again, also it's a mix. So there's the mean age was under 18 in that group, but you had some plus minus 3 months either age.
But it almost looks like the saturation curve, it saturates at similar levels, the comprehension score, if they keep measuring it over a longer period of time.
Maybe
It
in time
improves.
they'll already lost some important learning ability.
Right.
Yeah. By the way, they do note that even at the youngest group, it's still inferior to the normal hearing people at that age. And by the way, in all of them, it does improve over time, since that's another point, that there is improvement, and also that given age, kids do get better at this sort of thing. But yeah, there's still a big difference between the normal and the not. But again, if you compare it to, say, the normal hearing of the 36-year-old month, it's huge disparity. Yeah? Hmm?
If the implant, the cochlear implant, at very early age, does the brain change and then they need to implant it once again after several years?
They don't go into that into detail. They said that they could be done as young as the age of 8 months, in which case, it's not a problem, by the way. It doesn't go into the brain itself, that depends on how you define it. It's inside the inner ear, and then it basically interacts with the nerve fiber, but it's not the ear, it's in it's not in the brain, it's inside the ear.
So change with age, for example, is there a difference between 1-year-old and 5 and 10 years old?
I would think so. That's actually something which they didn't go into in terms of implanting at a young age. They don't mention reimplantation, but I would imagine the organ would get a bit bigger between a young 1-year-old and a 10-year-old, but apparently it's not enough of an issue for them to start mentioning it. The only thing that really they do require upkeep checking on it, but really the external part is the microphone and the emitter, which just change the battery. important that it's very, very important in terms of to track longer. There's a philanthropist now in China giving the cochlear implants to some 10,000 kids, but there's no resources for, tracking and monitoring and tuning it. So there were a lot of people were saying that, it might not be anywhere near as effective as you might think. But again, this is a really ongoing process. By the way, all of the kids in the study also had therapy and treatment for the like. It's multi-step treatment.
So how many kids there are until this day with the cochlear implant?
Over numbers, I think there were about 300,000.
Calculated out. Wow.
There is in Israel a Bedouin village that all the great percentage of the kids suffer from that
Yes,
and they're still with cochlear
it's
implants.
very possible because there were something like 45 identified genes associated with loss of the inheritance, for example.
Well, let's move on. Thank you. בסדר, אני שומר עלייך, אני אחרון. Let's see, 23 minutes. Anything goes off. I didn't start yet, don't go. Go.
Okay, so hi everyone. My name is Sarah. I'm going to talk about the following paper, just recently published in Nature, and it deals with the role of the nasal system and brain area in the function of parental behavior. So let's begin with what parental behavior is, and basically it's the interaction between the adult organism toward the non-mature one in a way that is aimed toward caring and protecting the young. And it's common among many species, and it's presumably regulated by evolutionary conserved neural circuits because it's very important to the survival of the offspring. And it's different across species, across male and female. Female usually is the more parental figure, while the male is different across species. In male mice, species such as the one we're going to discuss here, the way that the males act towards the pups different across species, but also it depends highly on the sexual experience of the male. So a sexually experienced male will exhibit parental care, will nurture the pups and care for them, while the non-experienced ones, the virgin males, will not really be considered the father of the year to pronounce it this way. So at best they will neglect and ignore the pups, but also they can kill them at worst. So if we'll dig a bit more deeper into this phenomena, so this is about part of this study that they examined this behavioral switch in behavior, and what they saw here, they let the virgin male mate with female, and then expose them to pups after different time intervals. So, and the dots are color coded. So red means that they attack the pup, blue is ignore, and green is retrieve them to the nest. So when the mouse was mated with a female, and then 2 days later, after the mating, was exposed to pup, he behaved in aggression manner. He attacked the pup as like the virgin male, and so it was true also for around 2 weeks period after mating. But if they waited around 20 days and more, which is the time it takes for the female to give birth to the offspring, then we'll see this behavioral change, and there is a gradual reduction in the aggression and switching towards parental behavior. So this change in behavior occur as a response, as a corresponding to the time of the birth of the offspring. So not.
So they were together with the female after the mating?
No, they were separated. They were separated, and each time was exposed to the pups after different times.
The pups after 2 weeks, is it his own pups or?
No, it's not, but you can't know it. This is the meaning of, this is the evolutionary so-called advantage, because it could be his pups. But before this time, it can't possibly be his pups. And so it's not only a dramatic change in behavior, it's also modulated in a very smart-like way, if you think of the evolutionary advantage. And you're probably all thinking, maybe you ask yourself, so how does this mechanism work? What modulates this change in behavior? And this is exactly the answer that this paper is discussing. And as a first step of answering this question, so as a first step, they examined the role of the vemeronasal system, which is the vemeronasal organ is this one located over here. And as we discussed it in Yoram's lecture, its function is to recognize the chemical signal that is specific for the species. And the author of this paper thought that he played some sort of role in the modulation of this behavior. And in order to examine, to verify the claim and to further explore it, they conducted the following experiment. They used a genetic manipulation which they developed previously in their own lab in previous studies. And what they basically did is knock out for the TRPC2 channel, which is a specific channel expressing only in the VNO nerve. And they created, by doing so, they created a line of mice without functioning signaling from the VNO. So, and then they checked those animals to see how they react to pups now. So we can see here the different groups of mice. This is the control virgin male, which normally will attack the pups, and as we can see, in this case, it's also attacking the pups, acting aggressionally in most cases towards the pups. But when you look at the virgin male without the functioning VNO, we see a strong reduction in the aggression towards pups and emergence of parental behavior. And the emergence of parental behavior is also is visible in here. There is more retrieval of pups into the nest compared to the control. Still less than female, who is more maternally and caring, but there is a big difference. And there is also more time spending in activity of parental activities such as grooming and crouching and nest building, and more time spent in the nest. So now it's pretty much supported their claim for the role of the vemeronasal system. There is some it's pretty much supported their claim, and their hypothesis now was that okay, the VNO is involved, but maybe it's modulate higher order circuit in the brain, and they wanted to look for this central circuit in the brain. And they did it by looking at signals that indicate activity during the parental activity. So first of all, they used the CFOS, which is a marker for neural activity, and they compared the neural activity among animals after exhibiting parental behavior and non-parental behavior. And they saw that in virgin female and father, both of them are groups that exhibit parental behavior. They saw a similar pattern of activation, mainly in the medial preoptic area, which is this area located over here in the hypothalamus area. And this was strongly activated after parental behavior in those two groups. As you can see, for the red dots represent the CFOS. But it was silent in the virgin male, which exhibited only pup aggression towards pups and not parental behavior. So they found an area that is now show a different pattern of activity for parental and non-parental activity, which is good, but still this area is not very specific. It also modulates other behaviors such as sexual activity, temperature regulation, etc. So it wasn't really specific and exclusive for parental behavior. It wasn't, if you said, the holy grail that they were looking for. So, and as you can see here, there is also activation of this area after mating. So it wasn't exclusively for parental behavior. So they kept on digging in, and this time they focused on this area, which I just show you. They had a really good reason to, because it showed a different pattern. And they used now catfish, which is a method they developed in order to identify protein and materials within the cells by using a specific marker for the mRNA of this protein. And they used several of these markers for every neuropeptide and neurotransmitter that are known to express themselves in the medial perioptic area. And as expected, and they conducted this analysis for animals for different kind of activity, not just parental behavior and non-parental behavior. And as expected, they saw a different group of cells activated after different kind of activity. And the galanin neuropeptide, neuron that express galanin neuropeptide, was activated after parenting activity, but much less after non-parental activity in others. So they now have a group of cells, the galanin-expressing neurons, that are activated. So it's not that they are not activated in other activity, but much less. And we can see here from those analyzed that a great percentage of the galanin-expressing neuron in this area was activated during the parenting behavior, but not in other. And a large amount of the cells that was activated was galanin-expressing neuron. So we now have a new rising star in this study, and they wanted to further examine it and confirm if it really is part of the circuit, the central circuit that they were talking about. So they say, okay, if it controls this behavior, let's disrupt its function and watch and examine what's going on after. And they used, so in order to do it, they used transgenic mice, which express the galanin. They had like a short sequence next to the promoter of the galanin, and in all the transgenic mice, and then they injected virus who was targeted to this sequence and contain also a toxin. So they eliminate the cells expressing galanin, but the other cells remained intact, and they injected it only in the medial perioptic area, so only those cells was infected. And then they measure the behavior towards pups. So what we can see here is father and virgin female, which normally will exhibit parental behavior. And we can see here that there is reduction in parental behavior. And that means that they spend less time engaging in parenting activity, such as crouching, pup grooming, nest building, and overall parental interaction with the pups. But the more convincing evidence, at least to my view, was that this reduction in parental behavior was correlated with the number of galanin cells that was left intact in this area. So this is, again, the same color-coded as we saw earlier. And we see here that when there is a small amount of cell remained in this area, there is either aggression or ignorance from the pup, whereas there is a lot of cells intact in there. The behavior will be parental, as will be observed in the control group. So after establishing that damaging those cells affects reduce parental behavior, they now wanted to go further into this matter and activated the cell. So they used optogenetic tools in order to do this, and they used the same transgenic mice, only instead of injecting the virus containing toxin that targeted to the CRE sequence, they injected virus containing the channel rhodopsin. And all those cells, as you can see here, not all of them, a large fraction of them express the channel rhodopsin, and also they inserted optic fibers in order to activate them, and they measured the response. And this time each animal was exposed to the pups both with and without the stimuli. Also there was a control group without the channel rhodopsin. And when they measure their behavior, they let them be with the pups in the cage and approach the pups. And each time the mouse approached the pups, they saw it happen. Now here we see that this is without the stimuli. So he approaches the pup 19 times. And out of this 90 times, 80 times he attacked him. But when we added the stimuli, so he approached the pup 18 times, but he only attacked him twice, sorry. But there is a very strong reduction, and not only did he not attack him, he also groomed him instead. So there is a very strong switch from attacking to grooming. We can also see it here, and also that the non-stimuli protocol, the result is very similar to the control, to the one without channel rhodopsin. Whereas you add a stimuli, you see a very strong reduction in the aggression and emergence of grooming. And this is the result from the activation. So the blue dashed line is the light activation, and the yellow surface you see underneath is the grooming. Red is attacking, and you can see that most of the time after each light stimulation, there was a grooming activity with the pups, and one that did not occur in the control group. They're the only attacks the pups. The red means attacks. And the interesting thing is that it was only true about grooming. They haven't saw any other parental activities such as the one we talked about earlier, other than grooming. And not only that, also in the fathers, when they tested the father with the expressing the channel rhodopsin, they saw that, and they normally exhibit parental behavior. But when you add the stimuli, so they also had more pup grooming, but it came on the expense of pup crouching. So something here wasn't really adding up to the fully model that they proposed, but still you can explain it with different kind of connection. But there was some question remained unanswered. Also, it affected other activities such as locomotion, and it increased the aggression between males. And one might say that maybe this is just showing general increase in aggression, and not something that is pup-directed aggression. So some of those questions remained unanswered. They suggested that maybe the male-directed aggression was because it declined because they were so busy looking for pups to groom that so I don't know. I wasn't fully convinced, but it could be some other circuit involved, and it could be that the galanin expressing neurons is also there is subpopulation within it that control different kind of activity. It also can be the possible. So, how much time?
Yeah, well, here we go.
Okay.
7 minutes.
Woo! So I can go back.
You can go back and forth.
Okay.
Do whatever you want. 7 minutes are yours.
Okay.
Question if you want.
Yeah, you can. If you want, you can. I can also move along.
Just technical. Is crouching considered something like a paternal behavior?
Yeah, crouching is a kind of posture changing in a way that it's covered the pups to help maintain the body temperature. Those are all parameters that also been found in other studies before. It's not something they invented. Okay. So also I want to mention here regarding because I have more time, regarding the galanin expressing neuron. The interesting finding in here, over here, is that the amount of cells expressing galanin both in female and in male was the same, meaning it's not something structural in their brain in the amount of cells that modulate the behavior. The same cells are there, but they're activated in different manner. So it also suggests some sort of neural circuit that is modulated by some sort of mechanism. And also, okay, never mind. So let's summarize what we saw so far. So the disrupting of the VNO system indeed had effect on the behavior, and we saw that virgin males expressing aggression towards the pups. But after mating, this aggression turned into parental behavior. So, as we asked before, what turned these pup killers into loving, caring father? So this is the model that they suggested, and the train is just my metaphor, so flow alone. So when the virgin male receives the output from the VNO, it's caused the activation of the path leading to aggression this way. And remember when there used to be this old train with the pull bar that you can change the tracks? So in the same manner, after mating, the galanin expressing neuron is switching this behavior, this path, into a second path leading to parental. So they inhibit the aggression and excite the parental part. And yeah, of course, it's not that simple, and there was also some suggestion along the way that maybe there is more complexity and maybe it's more similar to this. Yeah, possibly. But but they claim, and I personally think I believe them, they did manage to uncover a part of these tracks. And even if it's a fraction, this is can teach us a lot and contribute to the knowledge we have on the modulation of complex behavior, of social behaviors, and the way they are modulated. So, yes.
I hope I didn't miss you when you mentioned this, but did they try and explain the time scale of the behavioral change?
What do you mean?
Because you showed in the beginning that it takes about 20 days.
Yeah.
And this.
How long it lasts, you mean?
No, like they had sex 20 days ago, but they changed their behavior only 20 days later. So what?
So this is the mechanism that's supposed to explain it, but the time characteristic, it could be they didn't fully answer why it takes so many times, but what it implies is it's something more complex and a very smart way to manage this behavior, because you don't want the father to attack his own children, his own offspring. You want him to attack other, and so increase the. I personally don't, but this way he can increase the odds for his offspring to survive. So this is what it implies. It could be the neuropeptide galanin. They don't fully understand his function. It could be that it acts as a kind of hormone, and so maybe it takes more time and so on. It could be that he modulates other areas that control hormones, and there could be other processing that occur during this time. We don't know. So, yeah.
May we go back to the slide where they compared the mating and other behaviors?
With the CFOS?
Yeah,
And
before
this one.
Yeah.
Yeah.
So in the enrichment of galanin in CFOS and enrichment of CFOS in galanin,
Yeah.
the percentage in the first graph goes up to 50% under parenting. And so that is around, it's higher than 30%, 30 to 50%.
Yes.
And that's already higher than the enrichment of CFOS in galanin.
Yeah, because you can't, they couldn't label both of them. They couldn't, they could label, but they couldn't differentiate between the two labeling. So it's when the new, so wait, maybe I'll just, they looked for double labeling of cells that expressed, in this case, both the galanin and the CFOS, because then it will mean that this cell is expressing galanin and also activated in this behavior. So the first figure, it's like the galanin expressing, the marker for the galanin, plus the FOS. And it's divided, they had like a kind of, and it's divided for the FOS labeling, cell that was the label with FOS, and with neuron, which is a marker for neuron cell. So, but the one that was labeled with the neuron, it couldn't be also labeled with the, so this is why the percentages are different, I think. This is what you asked?
Okay.
Yeah.
Yes.
So maybe I missed it, but did they control for diminishing aggression towards, I mean in general?
Yeah, this is what I said in the end, that like in other cases it was the same, but in the optogenetic in
So
this
so
part.
they were less aggressive towards fox, not
Yeah,
humans.
no, but it one of the problem in this part. It was also less aggression toward other males, which maybe there is a general decrease in aggression, or maybe there is activation of other cycles in there.
You talk about the circuitry between the gala neurons and other places, or from the VNO to the NBRA?
They mentioned that they could be. They didn't further investigate. They just suppose that either it acts directly as a kind of hormone, or it activated other hormonal area or other circuits.
Boom. Any more questions? Afla. 1:10. We are back. Right? We have one more. Here, here.
Yeah.
לא, יש עוד תיקים.
יפה, אחלה מאמר, זה לא היה מעניין.
כן, היה מעניין. אפילו שזה הכריח אותי ללמוד
אפילו? דווקא בגלל, זה עוד יותר טוב.
כן, אבל אני מקבלת משוב מתישהו?
כן, אפשר לשבת ביחד אחרי היום, גם
אני אשמח.
של הנורופפטיד. זה הורמון בתוך
כן.
נוירומודולטור.
כאילו היה לי קל מאוד.
מודולטור זה תרגום
מה זה?
כאילו היה לי קל מאוד להתרגל.
כן? לא, אבל היה טוב.
לא איזה
תודה. על מה אתה מציג עכשיו?
החבריהם,
על ציר...
משהו computational כזה?
לא, זה לא כל כך, כאילו מחפשים את איזה קשרים יש באזורת האמיגדלה, כל מיני קשרים בין נוירונים שיכולים להסביר מה קורה בציר זה.
מעניין, טוב.
כן. תקשיבי, בטח.
אין לי ברירה. לא, לא, בסדר.
התאים הספציפיים האלה אני לא יודע, אין לי מושג
מה זה על
האקטיבציה הסינפטית שלהם ומה המשמעות שלהם.
Here, did you find this?
Yes,
Your tweet?
I
Okay.
did, thank you.
sum up the course in 5 minutes. If you, Alan, if you have any particular comments I should take into consideration because I'm continuing on this course. And that's it. It's the exam, and finito la commedia.
Okay. So since I'm the last presentation given, then I'd like to wish you all a happy vacation, and I hope that you all see beaches like this one on your vacation. I don't know. This is from the internet, but it was very beautiful. But for the next 25 minutes, forget about this nice beach, and we'll talk about this paper named Amygdala Interneuron Subtypes Control Fear Learning Through Disinhibition, which really tells you nothing at this point, but hopefully by the time I'll be done, you guys will understand what I'm talking about. This is a Nature paper that was published just this year, 2014. So we'll talk about the basolateral amygdala. It has been identified as a key brain area that is involved in fear learning. And we'll try and understand the mechanisms within the basolateral amygdala and how they enable fear acquisition. So the main players that we'll talk about that take part in this process are the paravalbumin and somatostatin interneurons. And this is the last time that I'll say their names. From now on, I'll just say PV and SOM. What you should know is that the PV interneurons form synapses near the soma of the target cell, and SOM form their synapses at more distal dendrites. This is also something that they showed in the paper. So what we see here, the y-axis is the number of contacts on the soma. So we can see that SOM contact the soma in average about 8 times, while the PV interneurons have synapses on the soma on average about 25 synapses on the soma. And on the dendrite, it is reversed. So about 100 synapses on the dendrite and, I don't know, 350 synapses on the dendrites of the target cell. Yes?
How many SOM and PV neurons do you include in this, or just one?
Just one. So this is an average of one interneuron and how many synapses it has. Oops, sorry. Okay. And so these interneurons, their target cell is it's not just one specific cell. It could be a group of cells, but what they call it in the paper, they talk about principal neurons. Principal neurons is just a term for neurons that their soma resides in one particular area, and their axons go outside of this region. So basically, these principal neurons are the output of the basolateral amygdala. Okay, so we have the PV interneuron, which mostly inhibits the soma of the output, and the SOM interneuron, which inhibits the more distal dendrites. And this is the computation done in the basolateral amygdala, and that controls the output that goes away from the amygdala. So this is what we'll talk about. If I'm doing this. Okay. So when we're done, you should be able to understand and explain the underlying mechanisms governing the unconditioned stimulus stage of fear acquisition, and the underlying mechanisms governing the conditioned stimulus stage of fear acquisition. And this will be in the final exam, so please listen carefully. Okay, what did they do? So I'm guessing that you all know what's the fear conditioning paradigm, what happens. I'll go over it very quickly. Basically, you have a conditioned stimulus, which can be either a tone or a light or whatever. In this case, it's a tone that was given, and then some kind of aversive stimuli, in this case a foot shock, and you put the two together, and whomever learns that the tone is associated with the foot shock, and then when they just hear the tone, they'll be afraid. So they learn to associate the fear and the foot shock. So we all on the same page, right? Good. So we have the control group. They were given one tone
or a different tone, and for every tone they were given a foot shock. And then we had a lot of different groups, um, but so one group, I'll try to. This is really simple, but I'm not very good at explaining this, so I'll try and do a good job. But if you don't understand, let me know. So we have control we all get. The other group, they will either express channelrhodopsin in their PV neurons or arch in their PV neurons. One group. So this is already two groups, and then we have another two groups that will either express channelrhodopsin in their SOM interneurons or arch in their SOM interneurons. And now we take these four groups and we either give them the one tone, which will be the same as the control group, with some kind of stimuli, either inhibitory or excitatory stimuli, which will either inhibit or excite one of these cells, and we give the foot shock. Okay? And then the other tone will be exactly the same as the control group, and we will not give any light stimulation. And one last thing, the light stimulation can either be just during the conditioned stimulus or the unconditioned stimulus or throughout the entire process. Okay?
The other tone here is just for control inside this.
This one?
Yeah.
Yeah, so this is basically just to make sure that, because we've manipulated the system, so you want to make sure that the fact that you added channelrhodopsin or whatever does not cause deficits in learning just by itself. Okay, and then the following day, the tones, either tone A or tone B, they call it 1 or 2. Tone 1 or 2 was presented to the mice, and they measured their freezing responses. So if the mice froze a lot, that means that they learned to associate the tone, the conditioned stimuli, with the aversive foot shock. And if they froze less, it means that they learned not as good. Okay, so first I wanted to make sure that PV interneurons actually participate in this fear learning process. So what they did was, in the first day, they either gave one tone with no optogenetic stimulation and did the entire process of fear acquisition or fear learning, or they photostimulated the PV interneurons, excited them throughout the entire process, and they compared the two groups. So we can see that when for the tone that was not presented with any photostimulation, this is the baseline. Okay, this is the first day before any learning, and we see that when they're presented with the first stimulation, it looks the same for both control and other group, and for the second tone that was presented with light stimulation, we see that the mice actually learned less. Okay, they froze less, meaning they associated the tone with the foot shock less.
But you have also different baselines.
Yeah, it's not a big. It actually, so it means that they actually learned better, right? And here they learned worse. So it's even in their benefit. The baseline, they would say, they didn't really talk about this, but I'm guessing it's not a big difference. And anyways, it helps them. Okay, so we do know that PV interneurons take part in this process, or we can speculate that they probably do. Now they wanted to check the underlying mechanisms for just the unconditioned stimulus. So what happened? So first, this is just before any intervention. They just gave the foot shock and they measured the responses in the PV interneurons and the SOM interneurons. And we see this is frequency, okay? So we see that when the foot shock was given, there was a decrease in the firing rate of both the PV interneurons and the SOM interneurons.
So they're recording from the PV interneurons while they're doing the fear condition test?
Mm-hmm. Okay, so both interneurons are firing less. So we have inhibition of both the PV interneurons and SOM interneurons. This in turn disinhibits the principal neurons. Remember, these are the neurons that their axons are going away from the basolateral amygdala, and then we get a freezing behavior.
This is from which stage? The training, the first
So yeah, this
or
is
at
when
the
you give them a foot shock, you measure the responses of the PV interneurons and the SOM interneurons. You just measure their frequency rate.
But
They
now
did a
they
whole
know
cell.
to, I mean, it's the first time they're experiencing frequency, right?
Yeah, I mean, this is whenever you give them a foot shock, you see that it is decreased. But this is during the learning phase. Yeah. So if both PV neurons and SOM interneurons are firing less, what would happen to the principal neurons? Just to make sure that we all understand, they will fire more. Right. Okay, and then they also intervened with the system. So again, remember as we saw before, they for one group they excited the PV interneurons, and for a different group they inhibited them only during the unconditioned stimulus. And then on retrieval, they saw that when they inhibited the PV interneurons, the mice actually froze more. Okay, so this is a difference from baseline. 0, this is how the control would freeze, the amount of time the control would freeze. And if you inhibit the PV interneurons, they actually perform better. And if you excite the PV interneurons, they're not as good in the sphere acquisitioning path. Now they wanted to see what's going on during the conditioned stimulus. אתה יכול להדליק אותו? אתה יודע איפה? להדליק את המגן, אתה יודע איפה? יפה, אני רואה שאתה מחלק. תודה. So, okay, so now during the conditioned stimulus, again, this is the unintervened system. They give the tone while during the fear acquisition. They give the tone and they measure the responses of both the conditioned stimulus and of the PV interneurons. Excuse me. And we see that when the tone is given, the PV interneurons now are excited. So now they fire more. Before we saw that when the foot shock was given, the PV interneurons fire less. Now when they give the tone, the PV interneurons fire more. So we have excitation of the PV interneurons. We don't know what's going on with the principal neurons yet because we still don't know what's going on with the SOM interneurons. But this would lead to a freezing behavior in the normal animal. Then they intervened again. So now they gave either excitation or inhibition to different groups during the conditioned stimulus. Again, this is when the tone was given. And they measured the responses the following day just when giving the the conditioned stimulus. And we see that as we would expect, now exciting the PV interneurons during the learning phase, when we excite them during the conditioned stimulus part, we get an increase of freezing, so they learned better. And if they inhibited the PV interneurons when they gave the tone in the learning, that they actually learned less. Okay? You're with me? Okay, it'll be in the test, so. Okay, they did the same thing for the SOM interneurons, but unlike the PV interneurons, which were excited, they saw that during learning, when the SOM interneurons, when the tone was presented, the SOM interneurons actually decreased their firing rate. So the SOM interneurons are firing less. Okay, so we have, just to give you the picture, we have 3 neurons altogether. We have PV interneuron, which is inhibiting the principal neuron, giving the outputs from the basolateral amygdala. We have the SOM interneurons, which do the same thing, only they inhibit the dendrites. And we have the principal neurons, which will bring the outputs from the basolateral amygdala. So now during the conditioned stimulus, during learning, when a tone is given, the PV interneurons fire more, meaning inhibiting more the principal neurons, and the SOM interneurons are firing less, meaning they inhibit less the principal neurons. Okay? And again, they intervened with the system, and now they're either giving excitation or inhibition to the SOM, not the PV interneurons. Okay? And we see, again, as we would expect, we see that now when we're inhibiting the SOM interneurons, it actually helps the learning, and when we give on retrieval, when we give the conditioned stimulus, they actually perform better. Okay, so we have if we excite the PV, not these neurons, if we excite the PV neurons during learning when we give the tone, and later we'll check how well the mice learned, we see that the mice will learn better. And if we inhibit the SOM interneurons during learning, when we will see how well they learned, we'll see that they learned better. Okay, so we know that when we give a tone during the conditioned stimulus part of the fear acquisition, PV interneurons are excited, SOM interneurons are inhibited. We still don't know what's going on with the principal neurons because we have a reverse effect, right? The PV interneurons are inhibiting them more. The SOM interneurons are inhibiting them less, so we don't know what's going on with them. And there might be, we're thinking of perhaps there's a possible connection between PV and SOM interneurons. Why? Because we see that when one is excited, the other is inhibited. Okay, so they checked that. This was done in slides actually. Again, whole cell recordings. And what they saw was when they activate the PV neurons, there is actually a decrease. Okay, this is currents, but we see that there is an inhibitory input going into the SOM neurons. Okay, so what they propose is that the PV interneurons not only inhibit the principal neurons that take the information away from the basolateral amygdala, but they also inhibit the SOM interneurons. And they wanted, because again, remember that the SOM interneurons inhibit the dendrites, and we're talking about tones that are given to a mouse, and we were talking about fear conditioning. So they wanted to see if how well the SOM neurons, or if at all, how they inhibit the they wanted to see how they inhibit the input going into the principal neurons from the thalamus, which is where the auditory input comes from. So first they just gave the light, they excited the SOM interneurons. Okay, this is this blue light, what this means, and we see that actually there is an inhibitory postsynaptic potential that's going on to the principal neurons. Okay, there are a lot of neurons, so just, do you know of which I'm talking about?
Where is the recording not from?
Where?
It's from the principal neuron?
Yeah, so this is from the synapse that's going into the principal neuron, and we're exciting the SOM interneuron. So when we excite the SOM interneuron and record from the principal neuron, we see that it inhibits the principal neuron. Okay? When we just excite the thalamus, this is the black line. Okay, the thalamus brings auditory input into the principal neuron. So if we excite the thalamus, we see that there is a big increase in potential in the principal neuron. And if we put both of them together, so we excite the thalamus and at the same time we excite the SOM interneuron, we see that the input coming from the thalamus is actually decreased. Okay, so they wanted to show a connection between tones coming in and the ability of the SOM interneurons to inhibit the information of the tone that is coming into the basolateral amygdala. Okay, so hopefully this will make things a bit clearer. Oops. So we have the SOM interneuron inhibiting the dendrites, PV interneuron inhibiting the closer to the soma. And what's happening when a tone is given, the PV interneurons are being excited, remember? They inhibit the SOM interneurons, which in turn stops the inhibition to the principal neuron. Okay, so we get less inhibition coming from the SOM, but they also inhibit the principal neuron in the soma. So, do you have any guesses or educated guesses as to what will be the outcome of this? What will happen to the principal neuron? Will it fire more or less?
Less.
Less. Why?
Because
Because,
it's the tone.
okay, so that's what the researchers also thought, but surprise, what they checked was, okay, so I'll first explain what we see, and then I'll explain, okay, what's going on. So this is what we see here. The z-score is basically a difference from baseline. Okay, so zero, if it's on zero, it means that they're firing just as they would normally, and a positive increase meaning that they fire more, negative fire less. And again, this is the principal neuron firing. They gave the gray line is when they give a tone, a conditioned stimulus, and we see that there is an increase. Okay, we don't do anything; we just record from the principal neurons. We give a tone. We see that they actually fire more. Okay, so not only did they fire more, now what they did was they activated the PV interneurons. They activated these neurons. So not only that they're anyways activated because they give a tone, but they actually activated them more with channelrhodopsin, so increasing this process. Now, more inhibition going into the soma of the principal neuron, but also more inhibition going to the SOM, and there is actually an increase. The principal neurons actually fire more. Okay, so this is one thing that yeah.
The light activation is constant, so it's 200 milliseconds of light.
Yeah.
Neil, another question. The TV interneuron and the SOM interneuron. You said that when a tone is when you turn the tone, play tone, that the TV interneuron is activated.
When I give a
When you
tone,
play tone,
PV interneurons fire more,
yes.
SOM fire less because of this inhibitory.
Because of the TV interneuron. So
That's
does this mean that the tone is activating the TV interneuron but not the SOM interneuron? The interneuron is only activated by the TV, inhibited by the nerve.
you could guess that. Yeah, I mean they didn't check. The only input that they checked going into the cells from the thalamus was in regard to the principal neuron. But yeah, I mean they do receive inputs from elsewhere, so probably these PV neurons receive inputs from the thalamus as well, which tells them
And not the SOM.
They didn't do inhibition of TV and looked at SOM.
They did. It looks it's the same. I didn't put it because it was just
no. If they inhibit the PV interneuron and then play a tone and record from SOM, then you know if the SOM is inhibited because of the PV neuron.
They did, and they showed, yeah. They
So
did, and it's when they inhibited the you mean here or
no, not here, like
or
in the
for this?
beginning.
Just so I'll know.
It's not really important, so if you don't have time, it's not.
Okay.
It's just a control that they could have done. I don't know. They probably did it. Because
I think if I understand what you're asking, I think that yes, but we can talk about this later. Okay, and then so again, this is the same graph. This is the principal neuron. Okay, z-score. So again, positive. Yes. What does it mean?
It means that 23 minutes. You have a few more minutes.
Okay. So we see the same thing. Okay, now we excite the SOM, and instead of getting an increase to the tone, an increase in response of the principal neurons, we get a decrease. So the SOM inhibits all of the outputs going from the principal neurons. If you're interested in why I think this is happening, we can talk about this later. Okay, so our conclusions are, during an aversive stimuli, both the SOM and the PV interneurons are inhibited. This is the easy case. Okay, both are inhibited, meaning principal neurons are active, they get no inhibition, life is easy, and we feel the pain. During auditory cue, okay, this is the conditioned stimulus, PV interneurons are excited. In turn, that they inhibit both the SOM interneurons and the principal neurons. Okay, so far so good. Then this is difficult perhaps to understand the sentence, but I didn't feel comfortable changing it because I think otherwise it would not mean exactly what it should. So I'll read it and then I'll explain. Dendritic disinhibition override the effect of increased perisomatic inhibition. So this basically means that the fact that the principal neurons actually synapse right on the soma, one would think, as we all thought, that it
No,
was.
you need to integrate the total of the.
Yeah, okay, but I mean,
Just in case
just taking
one
this,
and one.
just taking this into account, you would think that it would count more. So, but still, the SOM inhibits stronger than the PV interneurons, and we actually get an increase in the principal neurons' activity, and we learn better, and life is easy. So for you to study, we know what's going on, or we know a little bit of what's going on during the conditioned stimulus and during the unconditioned stimulus when mice learn to do fear acquisition. But what's the gap? Well, what connects the unconditioned stimulus with the conditioned stimulus, and how does this happen? And I would like to thank Amir for some good pointers to this presentation, and that's it.
So, any further questions?
So, did they have any vision to use the light stimulus that they use?
Do they have any reason?
Do they say anything about why they do constant 200 milliseconds of light? Because that seems a little bit.
And not just during the conditioned stimulus, you mean?
Yeah, I mean they started before, it keeps on going, and also activation of channel opsin, as far as I know, is works best if you do it in bursts, and not if you do this constant activation. That's overkill, I think.
Well, I missed your question.
So if 200 milliseconds of constant light for channel rhodopsins, that's a bit overkill, right?
Depends what's the normal pattern of activation. You saw in the PV neurons, they're actually firing quite a bit.
Yeah, they're firing a lot.
So for PV neurons, it depends where in the brain. For PV neurons, continuous firing, I'm sure it's not continuous, probably it's the pulses of light or something like that.
So that's what I asked him. I think he said that it's continuous. That's why it's weird.
If you show your slide of the PV activation in the conditioned stimulus, this is when you show the conditioned stimulus from recordings from PV neurons.
Yeah.
So it's not far. Look at the top. This is what's naturally going on. So we're not too off. They're really within the physiological range.
Also, I have to say that PV interneurons. It seems that it's a very broad family. I mean, it's right. It
Broad
seems.
family? What do you mean broad family? Those are.
I mean that they're probably sub. They talk about this a little bit because they say that actually, so the increase. This is an average increase, but there were, I think, almost half, 14 out of 36 of the neurons actually were inhibited. So it's probably more complex. They just look at the average and.
I'm not sure it's a different subtype. I think maybe something in the circuitry is inhibiting them or something like that. But people are already, they don't have. They can't breathe. Yeah, they're overwhelmed from the subtyping of subtyping of subtyping. And PV is, it's what you would call, it's those fast spikers. Somebody who designed the system gave them a lot of power to spike a lot. So they can really handle quite a bit of spiking as compared to the principal nerves. Now I'm not aware of the specifications of the amygdala, but they do look like 200 milliseconds is not overkill.
And did they try to find a correlation or linearity between the inhibition or the excitation of the PV neuron and the strength of the sound?
No.
Of the tone?
No.
Because it could be that there is a relation between how strong is the condition and how much the PV
Yeah,
neuron.
all tones were given. Were similar except for it was different tone for the two different conditioned stimuli. But as far as you mean strength, you mean like volume?
Yeah, the volume.
So it was no, they didn't change it at all.
I mean, because it only the mechanism you developed in the one before, like the implant,
Yeah.
could be something different.
Thank you.
Okay, great. So last 2 minutes or 3 minutes or as much as you want. Comments to the content and framework of the course. This year we have added comments that I try to work or to either sit with you, with the people who gave talks and on their slides and talk on the slides, or unfortunately when I was away on email to give you comments. So the question is, was it, do you think, what can we do differently to improve the course? Because in many cases this is your first introduction to systems neuroscience. I feel that we are a little bit superficial with the talks, and the lectures that you give are more advanced than what you get in class. So I'm not sure that you really get the enough basics for the talks, and that you can jump into the water deeper and faster. So some of the teachers tell me that what we should do is increase the reading, so give you reading assignments, so you should read the chapter on audition, and then we can do a little bit more, go deeper into the topics, and that the lectures were a little bit superficial. So the question whether you feel the same way or not, or was it the same, good enough level, or what can we do to improve? Done.
Okay, regarding the extra reading, that was kind of one of the comments I would add. That we, for one thing, I would say that it really, really contributed to more things like we did with the one like wizard article, but say something like that before each one of the big topics. I really felt that would have contributed a lot, both in terms of discussion, or could even be added as a rule, and more in-depth understanding, and also to get a nice overview of the topic beforehand. Because actually some of the lectures I didn't feel were superficial. Some of them were slightly advanced, especially when they were talking about people's research, and I felt that it was,
Yeah, so the design was that we do basic, some of the features, and then we invite somebody to give a little bit more advanced topics. This was clear in the factory and auditory parts that I did. Vision is a problem. It's too much. I mean, we know so much about vision that we need to give more substrate, although I did hear complaints in the middle of the talk about the visual section. But also the somatosensation of that was basic. Mickey gave the basic, and Alex gave you a flavor for more advanced things. So I didn't completely get your comment. So you say to do more of these tirgulim like we did with you with discussions on papers. Yeah, that's actually this is something we did last year. I think we had three sessions. Yeah.
So the visual part had more reading, like you're saying,
Yeah.
maybe to do it. I don't think I feel any different about the reading made any difference to how the presentations were. I mean, don't feel like I understood the presentations in the visual part more because I had the reading.
You did not.
No.
Really? Okay.
I mean, maybe it's just.
So this format, you actually the regular format is fine with you.
Yes, but maybe I also had a little bit more background initially, so I don't know.
Initially. Okay.
So I actually already did the physiology B course.
Yeah.
So I think the same problem are for both two courses. I think the advanced talks they should be taken out of this
Completely.
courses completely, because we have a weekly seminar, we have a lot of different talks, and I think that in many ways we don't get enough of these out of this advanced talks. And I think that instead of giving empirical new research to present, maybe it's better that we'll present reviews, or nature reviews or science reviews, which is in a way might be repeating what's already been presented by the lecturers.
So who should present the reviews?
Students in your
So instead of advanced latest papers,